So before we can talk about rates of chemical reactions, we have to define what is the rate of a chemical reaction. Now let's go back to our same favorite reaction we used when talking about equilibrium. A physical chemist's favorite is nu A moles of A plus nu B moles of B going to Y and Z. Right, just to keep this completely general, we're not talking about any specific reaction here. And if we have a reaction that looks like this, how do we define the rate of that reaction? Now, a rate is a change in something over time. So the rate of speed, for example, is something in your car. How many miles per hour? So it's the change in the distance over time in that case. And when we're talking about chemical reactions, the rate is the change in the concentration of a species over time. So we give the rate, we call it V as a function of time. That's the symbol we'll use, V for velocity, you might think. And we can define it in terms of A, B, Y, or Z. Any of these we can use to define the rate. So we can look at the rate as the disappearance of A, and we scale it by the stoichiometric coefficient so that everything is being compared equally, right, in the chemical reaction. And a rate of change is a derivative. So we can say this is the derivative of the concentration of A. What's the change in A as a function of time? So dA dt. And we can similarly define this in terms of any of the other species present in the reaction, and we will get very similar equations. So for the reactants, you may notice I'm putting negative signs on these. That's because we assume this reaction goes in the forward direction as written, and so the reactants are disappearing as a function of time. If we write this in terms of the products, we instead have a positive value, still scaled by the stoichiometric coefficient, but still this same change in concentration over time. All of these, any of these should give you the same rate because they're all related to each other by the chemical equation. So this is how we define rates and the rate of a reaction, and we can do it in terms of anything. So when we write out the rate like this, the whole point of this chapter is that we can define what's called a rate law for a given chemical reaction. And this relates the rate to the concentrations typically of our reactants. So a generic rate law will look like this. Our rate, which again we have defined as V of t above, is equal to some constant k. We call this the rate constant. It's not, nothing very imaginative here. Call this the rate constant. And it's going to depend on the concentration of A raised to some exponent. In this case, we'll call it MA. And concentration of B raised to the MB. And just by looking at the reaction equation, we cannot know what these exponents are. Now, these are usually MA and MB, and you could have more than just two things, but we're just looking at our example reaction here. These are usually integers or half integers. And you need experimental data to be able to determine what this rate law looks like for any given reaction. So in the next chapter, we'll talk about mechanisms. And if you know the mechanism for reaction, you can usually figure out the rate law for the reaction. But generally, we don't. Some reactions we know the mechanism, some we don't. And so unless we know the mechanism, we can't determine the rate law just by looking at the reaction equation. And so just to give you some ideas of how much this can vary, even for fairly simple reactions, for example, the dissociation of this molecule, CH3CHO, I believe this is formaldehyde, can decompose to methane gas and carbon monoxide. And the rate law for this as determined experimentally is the rate constant K times the concentration of CH3CO raised to the 3/2 power. Right, and you look at this reaction, there's no obvious reason why it would be raised to the 3/2 power, just looking at this. As another example, of a reaction, another gas phase reaction, NO2 can react with carbon monoxide to form CO2 and NO. And the rate law for this reaction is the rate constant times the concentration of NO2 squared. And so what's obvious here is that CO, it doesn't even show up in the rate law. So for whatever reason, in terms of the mechanism, the concentration of CO doesn't matter for how fast this reaction goes. It has to be present, of course, or else you don't have a reaction, but adding more of it won't make the reaction go faster. So you need to determine rate laws experimentally, and you had the opportunity, or will have the opportunity, to do this in our lab for this class, where we'll look at a reaction equation to determine a rate law. So in the next video, we will look at what are the methods that we can do for determining these rate laws.